You see a headline claiming that 88% of American adults support expanding solar energy.
Right.
Or maybe you're just scrolling through your news feed, and you see a prominent politician's approval rating sitting at exactly 45%.
Mm-hmm.
And if you're anything like me, your very first thought is always, wait a minute, they didn't ask me.
Yeah, they definitely didn't call you.
No. In fact, they didn't ask my neighbors, they didn't ask my friends, or like anyone I actually know. So how can pollsters confidently make claims about hundreds of millions of people based on a survey of just 1,000 random individuals? I mean, when you really think about it, it feels like a magic trick.
It does, yeah. It feels like a complete sleight of hand. But there is a massive, incredibly rigorous engine of mathematics operating just beneath the surface of all those headlines.
And today, we're going to pull back the curtain on that trick. We've been looking through some really fascinating foundational research on statistical inference to figure out how researchers actually, quantify the unknown. Our mission for this deep dive is to basically shortcut the academic jargon. We want to uncover the hidden logic that allows us to separate a genuine statistical fact from, well, a lucky guess.
Right, because it turns out the math relies on a really beautiful paradox.
It does. But to understand how we can actually trust a poll, I think we first have to swallow a slightly uncomfortable truth. We have to admit that the number a poll gives us is technically wrong.
Yeah, that is the fundamental tension in all of statistics.
Right.
We are constantly chasing something called the parameter of interest. You can think of that as the true, absolute reality. So in your solar energy example, the parameter is the actual exact percentage of all 250 million American adults who support it.
But unless you have some kind of magical machine that can freeze time and simultaneously read the minds of every single adult in the country, that true parameter remains entirely unknown.
Exactly. It's completely invisible to us.
Right. So instead of mind reading 250 million people, we poll a tiny fraction of them, say 1,000 people. And that gives us our point estimate.
Right.
So if our poll comes back and says 88% of those 1,000 people support solar energy, that 88% is just our best guess at the invisible truth.
Right. It's just a proxy.
Exactly. But because it's a guess, there is always going to be an error. There's this gap between our poll and reality.
And that gap generally comes in two distinct flavors. You have bias and you have sampling error.
Okay, right.
Bias is the one people are usually the most suspicious of, and rightly so, It's a systematic tendency to over or underestimate the true value based on, well, human flaws.
Like leading the witness. The research we were looking at has this brilliant conceptual example for bias. Imagine you are trying to find out if college students support funding for a new sports stadium.
Oh, yeah, the stadium example.
Right. If you phrase your survey question by asking, do you support your school by supporting funding for the new stadium?
You've completely rigged the game.
Exactly. You are actively injecting guilt into the question. People are going to say yes just so they don't sound disloyal. That's bias. You can fix bias with better data collection, perfectly neutral wording, and, better methodology.
Right.
But here's the part that really gets me. Even if your wording is absolutely flawless, even if your methodology is perfect, you still have the second type of error, sampling error.
Yes. Because sampling error isn't a mistake.
Right.
It is just the natural, unavoidable bouncing around from one random sample to the next.
Right. Because one random sample of 1,000 people might accidentally grab, a few more solar energy enthusiasts than the national average, giving you an estimate that's maybe 1% too high.
Exactly.
But the next sample of 1,000 people might be 3% too low. So here is my big question for you. If sampling error is just this invisible, chaotic bouncing around, and we don't even know what the real answer is in the first place, how can we possibly measure the error?
Well, what's fascinating here is that you're touching on the fundamental question that almost the entirety of modern statistics is devoted to answering.
Really? The whole field?
Pretty much.
Yeah.
How do we quantify an error when we don't know the truth? To do it, we actually have to engage in a massive thought experiment. We have to imagine a hypothetical world where we actually do have the time, the money, and the power to poll absolutely everyone.
Okay, let's unpack this, because the thought experiment used to explain this concept is beautifully absurd. Let's pretend just for a second that we are omniscient.
Okay.
We actually know the true reality. Let's say the absolute truth is that exactly 88% of American adults support solar energy. To understand how our tiny 1,000-person poll behaves in the wild, we have to basically simulate reality.
Right.
Imagine taking 250 million pieces of paper, one for every adult in America. On 88% of those papers, we write the word support. On the remaining 12%, we write not.
It's a staggering visual, honestly.
It really is.
Yeah.
Now imagine dumping all 250 million pieces of paper into a stadium-sized swimming pool. You mix them all up perfectly. Then you put on a blindfold, reach into the pool, and pull out exactly 1,000 pieces of paper.
Mm-hmm.
You count the supports, divide by 1,000, and there's your sample proportion, your point estimate. But realistically, nobody has the time to mix 250 million pieces of paper.
Yeah.
We only have the budget to run one real poll. So what is the actual point of visualizing this incredibly tedious exercise?
The point is that while humans can't do this, statistical software can do it in milliseconds.
Oh, right, computers.
Exactly. A computer can simulate that blindfolded draw instantly. Let's say in the first computer simulated draw, the sample gives a point estimate of 89.4%.
Okay.
Remember, we rigged this hypothetical simulation, so the true answer is exactly 88%. So that first random sample was off by a positive 1.4%.
Just by random chance.
Just by chance. Then the computer runs it a second time, pulling another 1,000 hypothetical people. That time, it gets 88.5%.
Yeah.
A third time, it gets 87.8%. The computer does this mind-numbing process 10,000 times. And when you plot all 10,000 of those sample results on a graph, something magical emerges.
A shape.
A very specific shape. A histogram of all those results naturally forms a perfectly symmetric, soaring, bell-shaped curve.
Because extreme flukes are rare, right? Like
Yeah.
pulling 1,000 people who all hate solar energy is almost impossible.
Exactly. Most of the 10,000 samples clumped tightly right at the true 88% mark in the center. A few were a bit lower, a few were a bit higher, and almost none were wildly off. This bell-shaped curve is what statisticians call a sampling distribution.
A sampling distribution, okay.
There is a foundational philosophy in inference that I think captures the poetry of this concept perfectly. Sampling distributions are never observed, but we keep them in mind.
Sampling distributions are never observed, but we keep them in mind. I love that because in the real world, you only get to reach into that giant stadium pool one single time. You only have the budget for one real-world poll, but you have to imagine your single poll as existing inside that massive invisible bell curve of infinite possibilities.
Precisely. Understanding that your 1-point estimate belongs to this hypothetical family of estimates is the only way we can make sense of the data. And it turns out that beautiful bell shape doesn't just happen by accident.
Right.
It is the result of an ironclad law of the universe called the central limit theorem.
Okay, the central limit theorem. This seems to be the heavy hitter of statistical inference.
It is the absolute bedrock. The central limit theorem is the mathematical rule that guarantees our sample estimates will naturally form that predictable normal distribution, that bell curve. But nature doesn't give us that bell curve for free. The conditions are actually quite strict. First, the observations must be entirely independent.
Meaning one person's answer in the poll cannot influence another's. Right, so a simple random phone dial usually covers this. Or, if we step away from polling for a second, let's say you're looking at defects on a factory line producing computer chips.
Okay, sure.
An occasional random error on the assembly line is independent. But if the stamping machine physically breaks and ruins 50 chips in a row, those aren't independent errors. They're all caused by the same broken part.
That's a perfect example. Independence is crucial. The second rule is usually referred to as the success-failure condition.
The success-failure condition. What does that mean?
For the bell curve to form smoothly, your sample size needs to be large enough to capture the natural variety of the population. Basically, you need a big enough sample so that you'd expect to see at least 10 people who agree with your poll and at least 10 people who disagree.
Okay, here's where it gets really interesting, though. When you look at the mechanics of that success-failure rule, there is a glaring paradox.
Oh, absolutely.
To know if you expect at least 10 people to agree and 10 to disagree, you need to know the true proportion of the population. You need to know the real answer.
You do.
But the only reason you are running the poll in the first place is because you don't know the real answer. So how on earth are pollsters supposed to verify their math with a number they don't even have?
It's a fantastic catch, and this raises an important question about how we apply math in the real world. It highlights a brilliant, pragmatic workaround in statistics.
Okay.
Since we don't know the true population parameter, we use the plug-in principle. We substitute the invisible truth with the absolute best proxy we have, which is our single sample point estimate.
Wait, we literally just plug in our guess?
We do. If our single random poll says 88.7% of people support solar energy, we plug 0.887 into the formula in place of the true unknown reality.
Really?
Yes, we check to make sure 88.7% of our 1,000 person sample is at least 10 people, and that the remaining 11.3% is also at least 10 people. So in this case, that's 887 successes and 113 failures. Both are well over 10, so the condition is met.
I mean, I get it, but it feels a little like cheating.
It's an approximation, certainly. But mathematically, as long as the sample is random and reasonable sized, it has proven to be highly stable and reliable.
So because we meet those conditions, the data is independent, and the sample is large enough to pass the success-failure check. The central limit theorem basically grants us permission to assume our single pole lives inside a normal, predictable bell curve.
Yes. The math gives us permission to use the geometry of the bell curve. And once we have that permission, we can finally calculate exactly how much our pole might be bouncing around. We can calculate the standard error.
Standard error.
Right.
Now, in the research, there's an incredible way to visualize this.
Oh, the grids.
Yes, the grids. Figures 5.4 and 5.5, I think. Imagine plotting dozens of these bell curves. When you run a simulation with a really small sample size, like asking just 10 people, the distribution looks awful.
It really does.
It's chunky, it's skewed to one side, it doesn't look like a bell curve at all. It looks like a staircase that someone dropped down a flight of stairs. But as the sample size increases to 50, then 100, then 250, the shape smooths out. By the time you get to a sample size of 1,000, it is this incredibly tight, predictable, soaring bell shape.
Which physically demonstrates why a sample of 10 gives you a highly volatile estimate and a sample of 1,000 gives you a highly reliable one. We quantify that reliability using the formula for standard error.
Right, but I want to avoid reading algebra over the air. I don't want us reciting square roots and fractions.
Fair enough.
Translate the mechanics of that standard error formula for us. What is actually happening under the hood? Why does a sample of 50 produce a less reliable estimate than a sample of 1,000?
Think of the math behind standard error like a seesaw.
Okay, a seesaw.
On one side of the equation, you have your sample size and the number of people you polled. As that sample size gets heavier, as you add more and more people to your poll, it pushes the other side of the seesaw, your margin of error, down closer to zero. More data inherently means less variability.
Okay, well, that makes intuitive sense. Ask more people. Get a better, tighter answer. Problem solved. Just double the sample size and you have your error.
Well, up to a point, it's not a straight line.
Oh, really?
Because of how the math works, there are diminishing returns. To cut your error in half, you don't just double your sample size, you actually have to quadruple it.
Quadruple it?
Yeah.
Wow.
Yeah.
That's why pollsters usually stop around 1,000 people. Polling 4,000 people costs 4 times as much money, but only gives you a slightly tighter estimate. It's just not worth it.
That is fascinating. It's an economic cutoff as much as a mathematical one. But the mechanics of standard error hold a second, much more surprising secret, don't they? It's not just about how many people you ask. It's about what they actually believe.
That's right. The natural variability of a poll changes based on how divided the public is. If you look at the mechanics of standard error, the variability actually peaks. It hits its absolute maximum when public opinion is split exactly down the middle, 50-50. Okay, wait, I want to make sure I'm wrapping my head around the why here. Let's think about it intuitively. If an issue has 99% agreement, like let's say polling, if people enjoy breathing oxygen,
Right.
almost every single random group of 1,000 people you pick is going to look exactly the same. They're all going to say yes.
Yeah.
There is virtually no room for variance between sample A and sample B.
Exactly.
But if a population is deeply divided, split exactly 50-50, every single person you poll is essentially a coin flip.
Yes. And 1,000 coin flips can easily yield 520 heads one time and 480 heads the next. A 50-50 split maximizes the chaos in the system.
Wow. So it is mathematically harder to get a precise read on a highly divisive issue than it is to poll an issue where 80% or 90% of people agree.
It absolutely is.
That perfectly explains why polling in a swing state during a deadlocked election feels so incredibly volatile and chaotic compared to polling a universally popular policy. The math literally punishes us for being divided.
It does. When public opinion is near 50-50, the natural sampling error is at its absolute wildest.
Okay, so we've got our point estimate from the poll. And thanks to the central limit theorem and the mechanics of standard error, we now have a measurement of how far off our poll might be. How do we communicate this to the public? Because We definitely shouldn't just hand them our point estimate and pretend it's the absolute truth. No, no, reporting just the point estimate is scientifically irresponsible. You are presenting a single guess as a hard fact. This is where we make the vital leap from point estimates to confidence intervals. So, relying solely on a point estimate is basically like trying to guess someone's exact weight down to the decimal.
Right.
If I look at you and guess you weigh exactly 163.4 pounds, I am almost certainly going to be wrong. It's a useless guess. But a confidence interval is like guessing you weigh somewhere between 150 and 170 pounds. I give myself a reasonable buffer, which makes my estimate actually useful.
That's a great way to frame it. The foundational research we were reviewing uses a slightly different analogy that I think is highly evocative.
Oh, the fishing one.
Yes. They say using only a point estimate is like fishing in a murky lake with a spear. You think you see a fish, you throw the spear exactly where you saw it, but the water distorts the light, the fish moves, you are probably going to miss. A confidence interval, on the other hand, is like fishing with a net.
I love that. If you cast a wide net into that murky water right around where you saw the fish, you have a very good chance of actually capturing it. A confidence interval is that net. It represents a range of plausible values where we are highly likely to find the true invisible population parameter.
Exactly.
Okay, I get the net analogy. But how do pollsters actually decide how wide to cast that net? If they cast it too wide, like saying, I predict between 0% and 100% of people like solar energy, well, the poll is useless.
Right, you catch everything, so you learn nothing. To weave the net, we use the standard error we just calculated, and we rely on the predictable geometry of the bell curve.
Because we checked the conditions earlier.
Right. Because our sampling distribution is a normal bell curve, we know its shape perfectly, and mathematical law dictates that 95% of all data points in a normal distribution sit within roughly 2 standard deviations of the center. 1.96 standard deviations, to be exact.
So you take your point estimate and you extend your net out by about 2 standard errors in both directions. And that gives you a 95% confidence interval.
Correct. But if we connect this to the bigger picture, I think we really need to clarify something. Because 95% confident is one of the most widely misunderstood phrases in science and in the news.
Oh, absolutely. People hear 95% confident and they think, oh, there's a 95% chance that the true answer is inside my specific interval. But that's not quite right, is it?
It's a subtle but crucial distinction. The parameter, the true percentage of people who support solar energy, is a fixed number in reality. It's not moving. It's not a game of chance. What 95% confident describes is not your specific poll. It describes the process of polling.
So imagine we throw 25 different nets into that murky lake. We take 25 different samples and we build 25 different confidence intervals.
Right. If you visualize those 25 nets, the true parameter, the invisible fish, is sitting perfectly still in the water. Out of those 25 nets you cast, 24 of them will successfully overlap that fish. They catch the truth. But one of those nets, one of them completely misses. It lands too far to the left or too far to the right. It was just a weird, randomly unlucky sample.
So when a pollster hands you a 95% confidence interval, they don't actually know if their specific net caught the fish or if it's the one that missed. What they were telling you is, hey, I used a net weaving process that works 95% of the time.
Exactly. You are confident in the netting process, not necessarily the single net you happen to be holding at this exact moment.
And this matters to you, the listener, in a very real, tangible way. I mean, this deep dive isn't just about hypothetical solar energy polls or political approval ratings. These concepts are universal. When a factory engineer tests 212 computer chips to see if the defect rate on the assembly line is spiraling out of control, or when public health researchers check 800 homes to see if there are elevated levels of lead in the city's drinking water, or when economists survey Americans and find out that 322 out of 765 adults couldn't afford an unexpected $400 expense without going into debt. They are all doing this exact same math.
Every single one of them.
They're all throwing spears into a murky lake, calculating the standard error to understand the chaos, and building a 95% confidence net to quantify the massive uncertainty of the real world.
The variables might shift slightly depending on the specific setting, but the philosophical foundation remains exactly the same. Imagining the sampling distribution, verifying the conditions of independence, applying the central limit theorem, and casting the interval, it is the absolute bedrock of statistical inference. It is how human beings pull truth from chaos.
So what does this all mean? Let's recap the journey we just took. We started with a single, flawed point estimate, our one real-world poll. We learned to imagine its invisible hypothetical twins forming a massive bell curve called a sampling distribution. We verified that we could actually do the math using the central limit theorem and that clever plug-in trick, substituting our guess for the truth. We discovered that our error gets smaller with more data, but gets wildly larger when the public is split 50-50. And finally, we traded in our spear for a mathematical net, allowing us to confidently capture the truth in a very murky world.
It is a truly remarkable system.
Yeah.
But there is a final lingering thought I'd like to leave you with, building on everything we've just discussed. We established that the gold standard for all this inference, for the political polls, the medical studies, the quality control checks, is 95% confidence.
Right.
That means 95 out of 100 times the networks. But it also means that 1 in 20 perfectly executed, mathematically flawless studies will completely miss the true population parameter. Not because of bias, not because of bad methodology, purely by random, unavoidable bad luck. As you consume the news today, as you read the headlines and the latest groundbreaking studies, ask yourself, how much of our accepted, bulletproof knowledge is quietly sitting in that unlucky 5%?
Man, it makes you look at every headline just a little differently, doesn't it? Just keep your eyes peeled for the murky water and always check the size of the net.